Well, hello. My name is Sunil Agarwal. I'm a program manager with SQL Server team. And today I'm going to talk to you about operational analytics. This is a very exciting addition to SQL Server from our side, and wanted to share the benefits and the complexities that are associated with this technology. Before I begin, I wanted to know how many of you were in the session with Sean and Rohan yesterday. Okay, approximately 50% of you saw something about operational analytics. And this is something I want to take a double click on the technology and go down a little bit so that you understand what is involved. I've been with Microsoft for 12 years, working only on SQL Server, and I've been involved with the column store technology for the last 2 years. And you will see there is an integration of this Okay, so this is hopefully okay. You can, yeah, right. So there's an integration of this technology both with disk-based tables that are traditional tables, as well as the in-memory OLTP tables. So I have a very simple agenda. I just wanted to get across the point of what operational analytics is and how we implement both with disk-based tables and columns and in-memory tables. So what is the definition of operational analytics? What is the value proposition? And how do we do that with disk-based tables as well as in-memory tables? So let me tease operational analytics apart into two separate words. I'm sure all of you know about these things, but it's just good to go through that, what it is. So operational refers to operational workload, OLTP workload, as you know. And some examples of operational workload could be you have an ERP system which is managing your inventory, or it could be your orders, or it could be sales. These are traditional ERP systems which are going through a lot of transactions, right? Like inventory control, those things are changing all the time. It could be machine data. It could be data coming from, say, factory floor, how the health of the different factories, what the margin of errors are they shrinking, things like that. Very important things they monitor. Other thing is the online stores. I mean, all of us have experienced online stores through Amazon or through Expedia to make travel arrangements, right? So all these things are transactions that are being kept in the system. And finally, the stock trades. So the key point I'm making is all these operational workloads are mission critical. If they are down, you're losing money as a business. So for majority of the cases, people have these operational systems in a high availability architecture. And also what you want is you want your transactions to be low latency, should finish quickly, and it should scale, because when the workload increases, you do not want your operational system to suffer in terms of bottlenecks so that it does not get the business that you want, right? So the key point about operational systems is it is mission critical, it has to be always available, and it has to scale, it has to have good response time and all good stuff. Now, if you look at analytics essentially means that I'm looking at the past data, the transactions that have happened. I'm looking at the past data, which could be by transactions in the operational systems, or it could be even social media in today's world, to identify some trends. It could be how my sales are growing. It could be which product is more popular, stuff like that. These things are important. That's one example of analytics. You can even use analytics to say, how does this decision that I made is helping in the market. So for example, if you have an ad campaign, you put an ad, you can see, did my sale increase because of that ad? Is it effective in terms of pushing for that product? It could be even analyzing the past and the current data, for example, for credit score. So the key point I'm making is that analytics bunches large amount of data, which you can use to take advantage in your business decisions. Now, the goals, of course, is to using this analytics knowledge to make improvements or changes in your business for better profitability, right? Simple goal. Now, I was looking on the web and I said, let me find some evidence how prevalent analytics is in today's world. I got this report from MIT Sloan Review. It is a bit dated. I wish I could get like 2015. And what you see is that businesses, increasingly so, like 37% in 2010 and 67, almost doubled. People are saying, I need analytics to have a competitive advantage in the marketplace. I mean, so I think it is for us to believe that the analytics is absolutely critical for business functioning in today's environment. So now question comes, how people manage both operational workloads as well as analytics workload. So I have a very simple example. This is a traditional operational workload where you have a presentation layer. I put a couple of users there, but it could be any input device. It doesn't have to be a human. So you have data coming in, user transactions, and it hits application tier, which could be scaled out tier, and ultimately it goes to the data tier, which in this example is a SQL server. So this is how the transactions are coming and workload is running, right? Now, if I want to do analytics on it in a traditional environment, what people do is they do an ETL job, right? I mean, you have your operational system. You are running a ETL job, which could be hourly, could be daily, could be weekly, and so on, right? So you bring the data in from your operational system, and you put into a data warehouse. In this example, I'm showing you SQL Server data warehouse, so you put that data, right? And then you can do analytics on it by using reporting tools and BI analysis, whatever you want. Many, many tools are available, so you can do analytics on it, right? If you want to go even more complex architecture, you can insert or embed SQL Server analysis services in that. So this is how typically people do analytics, right? Does this sound familiar? I mean, this is pretty much, I see a lot of nods. So this is how it has been going on. Now, there are some issues with that, and I'm sure you all know that, but it's good to iterate those issues. First, it is a complex implementation. Why it is complex? Because you have to have your operational systems. You need to do ETL. ETL sounds easy, but it is not easy, right? You need to figure out what data changed since last time I did the ETL. In many cases, you don't have that capability. A lot of people pull the whole database to the data warehouse because they don't know what changed since when, right? So it requires two servers. Now you have an ETL, operational system, and the data warehouse. You have two systems. Of course, there is licensing costs. There are two machines. And more importantly, you have two operations. I mean, you have to manage two servers, right? It gets complicated. Now, if you move away from the cost part, the key problem with this configuration is that you see older data. Because if I'm moving data on a daily basis, if I'm doing analytics on that, I'm already a day behind, right? Increasingly so, many businesses cannot tolerate that kind of latency. They want data now. I'll give you an example, right? Credit card transactions. I mean, all of us have gotten calls from credit card companies saying this transaction is a suspect transaction because they want to do analytics on the transaction that you did, match up with your profile and say this is not right, right? So you want to be able to respond to the fraud right away. So the data latency is a big issue, and that needs to be addressed, which is not addressed in this configuration. And what people do to address that is they say, okay, instead of getting data on a daily basis, I'm going to get data every hour, or I'm going to get data every half an hour. But the point is, there is latency, right? Now, so what you can do, how can you minimize the latency of your data? So first thing that you can do is have your operational system just like before, right? Your operational system. And now what you do is you add indexes in your operational workload which are specific to analytics, right? I mean, I've seen some installations that have created some more indexes so that I can do analytics in a more efficient way. Because analytics queries may require different kinds of indexes versus your operational workload. Now, when you do that, the challenge with that is it is adding overhead to your OLTP transactions, right? Suppose I added 3 indexes. I do an insert into an existing table, and I have 3 more indexes for my analytics. Guess what? I'm adding 3 more rows into those indexes, right? So this is more expensive. But you're doing that to get better performance for your analytics, right? So you are compromising the performance of your OLTP system or operational system to get better query performance for analytics. And now what you do is, once you have created those indexes, you can use the tools that are existing in SQL Server or even third-party vendors to do analytics, right? And also, if you want, you can even add SQL Server analysis services there. So the only difference that I see in this picture versus the picture before was there is an ETL involved. In this case, there is no ETL. So what it means is the key benefit that you get out of this is that you are doing analytics on the live data. And this is what operational analytics is. I mean, how do I do analytics on the live data? Now, this is all sounds very simple, right? You just do analytics and you're fine. But the things are, it is very challenging. And why? The key challenges are, first let me go through the benefits. Benefits are very important. The key benefit is that there is no data latency, right? I mean, all transactions that are happening in your system, I can do analytics on that right away, right? No data latency. It simplifies your implementation, right? There's no ETL involved, right? And no separate data warehouse. So there are huge benefits, right? The key point is, can we deliver to this promise? And my goal in this talk is to convince you with the SQL Server 2016, we have made significant improvement in delivering this promise in a very real way. Now, the challenges, I mean, this is something is not unknown to you all. The key challenges are, when you run analytics queries on this system, even though you have these indexes created, it is resource intensive, right? OLTP workload or operational workload touches few rows. I'm inserting a row, I'm updating some account. But analytics, I'm scanning millions of rows to do some analysis, right? So that means it is taking so many resources in my system, which, guess what? It will impact my operational workload, right? In many, many cases, operational workload, if it slows down, it hits the bottom line. It will impact your business revenue. Because imagine this, right? If Amazon service, I'm not able to place my order, some of us may not even place the order, right? We'll say we'll come back later, I lose the revenue there, right? So the key point is the operational workload is a holy cow. You can't really compromise on it, right? Very important point. And so I think the goal is a good solution should be the one that can deliver analytics to me without impacting my operational workload in a significant way. Okay, so that's the promise we are targeting. Now, the third thing, which may or may not be clear to a lot of us here, is when you create a data warehouse, you use special schemas. You use star schema. You use snowflake schemas, right? You have fact tables and dimension tables, because those schemas are optimized for analytics. Okay. Now imagine this. If you want to run your analytics on your operational system, operational system is not optimized for analytics, right? It has OLTP schema. So the question is, how do I run a analytics queries in a more efficient way on a OLTP schema, right? So these are the challenges. And in SQL Server, what we are done is we are combining some of our technology assets to give you not only a high-performing operational system and also a very good analytics query performance. Okay. So this is, as I said, is operational analytics. Now, in a formal way, operational analytics is running analytic queries concurrently with the operational data on the same tables. That's the goal, right? Now, this goal, of course, cannot meet all data warehouse kind of workloads. So clearly, if you have extreme analytics, which you are running like on terabytes of data, the operational analytics cannot meet that goal, right? Because those analytics are being run on a star schema pre-aggregated data. So operational analytics cannot meet that, right? So what we are providing with operational analytics is ability to run analytics queries on your system in an efficient way, right? Or other scenario could be if the data is coming from multiple sources. So what people have, which is actually a common case, where you have a data warehouse and you're getting data from multiple sources, then you do analytics on it, right? Operational analytics is working on one system, right? So if you have a scenario where you're getting data from multiple places, operational analytics is not the right scenario for your organization in that case. However, even if you're getting data from multiple sources, you may want to do some analytics on each of those sources, right? So it can still help you. You can do full integrated analytics by combining all the data. So now I want to switch to 2016. What do we have which can deliver on this promise in 2016? So the goal that we started off was it should have minimal impact on operational workload, because many customers we talked to, they said, if operational analytics impacts my operational workload, it's not a solution for me because I cannot compromise on my bottom line. I need to have operational workload running flawless. Okay. So the goal was, how do I provide a operational workload along with concurrent analytics with minimal impact? Okay. And our solution to that is we will get that goal using column store index. So on that note, I want to find out how many of you have used column store or familiar with column store. I see approximately 25% of you have heard about column store. So the column store technology is something that SQL Server introduced in 2012. It was called non-cluster column store index, long word. In 2014, we came out with a new implementation of column store, which is called updatable column store index, and it was available as a cluster column store index. And what I want to show you is that this technology, which is not unique to Microsoft, I mean, the column store technology is there in the industry and in the universities for a long time, okay? So the question is how well you adopt that technology into the product. And that's something that Microsoft has done extremely well. So we use column store technology to deliver industry-leading performance for analytics workload. So question is, some of you who do not know about column store, I want to have one slide to describe to you what column store index is all about. So what column store index is, it is a different storage format for the data. In a traditional system, what you have is you have the data stored as rows. I mean, this is a traditional, when you create a relational tables, you insert rows, you have pages, and each page has a bunch of rows, right? This is what I'm showing you here. And so this is how it is stored. Now, this storage format is ideal for OLTP workload, okay? Now, having said that, this format has been used even for analytics, right? I mean, if you look at SQL's relational data warehouses before SQL 2012, people were using row store only in a star schema format to deliver good query performance. It works fine, but the key point is it is not optimized for data warehouse workload. So what is column store? This is a one-slide description of column store. It's going to be very useful. So what we have in the column store is, instead of storing the data as rows, okay, I store the data as columns. So in this example, what you see 5 columns in a table. And what I'm showing you in those blue vertical bars are column C1, for example, column C2. So what I'm doing is I'm taking column C1, I'm picking some set of rows in my table, right? For SQL Server, it is million rows. So you take million rows and pick column 1. You store column 1 values for million rows together, okay? So what happens is when you have a column 1 for million rows you can imagine a lot of values could be similar, right? Suppose a column that was a state. A lot of us may have the same state. So there's a lot of similarity in the values. What it means is it can compress extremely well. So what we do is we take column 1, million rows, compress it, column 2, compress it, and so on. So when you see these columns, C1, C2, C3, C4, C5 in this example, they will compress differently depending on the data, right? So now, because it is compressed well, in fact, with column store, you can get, on average, 10x compression. It's such a huge compression. So it is 10x compression. So you compress that data very well, which means on a large tables, you save your storage in a very significant way. As I said, it is up to 10x. I've seen cases where it is 20x, 30x. I've seen cases where it is 5x, even 3x, depends on the data. So, but the point is, with the column store, you can store the data in a very compressed way. Now, so because of that, a lot of analytics queries, when they run, the key bottleneck is the I/O, because I have to read so much data, right? But now, if I've compressed the data so well, my I/O will be reduced by order of magnitude, right? So that helps your query performance. Second thing, which is the most critical point, you only fetch the columns that you need. Now, if you look about row store model, right? You have a row with, say, 50 columns. The reason I made 50 columns, because if you have a fact table has a lot of columns. It is a big table. So if I want to, say, do analytics on the sales for a certain product, if I was storing my fact table as a row store, I have to get all those 50 columns, even though I was only interested in 3 columns. You see that? Because I'm just interested in this product and the sales, right? But if it was stored as row, I need to get everybody else, right? With the column store, because we are storing each column separately, so I can say, okay, if I want to do aggregate on column C4, I just need to get column C4. I do not have to get column C1, C2, C3, or C5, just C4. So not only I got good compression, I saved a lot of I/O because of that. Also, I'm only getting the column that I need. So in the example that I'm giving, if I have to get the whole row, I'm getting 5 columns versus I'm getting 1 column, right? So if you assume all columns were similar size, I'm reducing my I/O another 5 times, right? But I'm just getting 1 column, right? So that's another important point. And the third thing is, because data fits in memory, we have done some optimizations for processing the queries in the column store format. And one of the common thing that we have done is called batch mode execution. I will not go through what that is, but with those kind of executions, we are able to run the query much, much faster. So all those combinations, like the highly compressed data, fetching only the columns that I need, and the algorithms that we have done to process that data, gives us a huge, huge benefit in processing analytics queries in a reasonable time. And for these reasons, column store is ideal for data warehouse. In fact, starting 2014, our recommendation to our customers is use column store for your data warehouse, okay? And we back that with the industry-leading benchmark. This benchmark came out in 2014, 415, when SQL 2014 was released. So what you can see is we did the benchmark on a 3 terabyte and 10 terabyte database. This was a TPCH industry standard database. And what you can see is we are number 1 in performance with column store, okay? And if you look at the graph on the right side, we are the lowest cost. So what you get with 2014 column store is the world-leading analytics query execution at the lowest cost. So this is the technology that we have for running your analytics in a very efficient way. So what we want to do for operational analytics is to combine the OLTP workload with the column store to deliver not only good operational workload, as well as good analytics performance. So that's the magic sauce. So now let's go into how we have done this technology with your operational workload. So what I'm going to show first is running. Was there a question there?
Yeah, so the price that you're really paying is on the OLTP insert. So if you had 25 columns on a row, you'd be writing 25 tables.
That's right. So let me, this is the column store question. The question is that you have 25 columns and now insert a row. Now the row, each column goes separately, right? So how do I manage that? So what we have done is when you land insert rows into a column store table, we do not compress each row. What we do is we collect a set of rows, and that set of rows is million rows for us. So what we do is you're inserting rows and rows and rows. We collect them in a row store format, which is transparent to you. I mean, you say this table, this fact table is a column store table for me, right? So you insert rows, it is going to a internal row store there, and once it crosses the threshold of million rows, we compress it. So the insert actually is, you don't pay that much cost on that, okay? So actually on that, let me just say, I have a presentation tomorrow on column store. I wish column store presentation happened before this one. So all this kind of things would have been gone through. So now let's talk about how we do operational analytics on disk-based tables in SQL Server 2016. Okay, so I'm going to give a very, very simple example here. So what I'm showing you is a OLTP table. I mean, of course, OLTP workload has hundreds of tables. I'm just giving one example, okay? So you have a table which is stored as disk-based table, and you have a bunch of B-tree indexes that you have for your workload, right? So your OLTP workload is running fine. Now, if you want to do operational analytics on it, so what we are saying is, all you do is create a non-clustered column store index, okay? Now, you see the structure is quite complicated, right? So what I showed, this is the question that I think you had. You see something yellow over there? This is something what we call as a delta row group. What delta row group is, it is storing the rows in the row store format. And periodically we compress them. So what you see in the blue are the rows that have been compressed, okay? So this is a non-clustered column store index. Now, remember we talked about the industry-leading performance. That was with column store, right? When I say column store, it includes even non-cluster column store because it is the same kind of methodology. So what you have is you just create that index, right? Imagine this. If you wanted to do analytics on your operational workload, we were talking about you create one or more indexes for your analytics. Now what you're doing is just creating a non-clustered column store index, okay? Now, the key points on this one is that it is updatable. The reason I'm underlining updatable is non-cluster column store index was available in 2012, but it was not updatable. So imagine this. If you had created a non-cluster column store index on your operational table, what would have happened? The table would have become read-only. No operational workload, right? Now, with 2016, the non-cluster column store index is updatable, right? So you're running your operational workload like before, it is updatable. So what you do is, if you have operational analytics scenario today, and you have created certain indexes to make analytics go faster, what we are saying is you don't need those indexes anymore, just drop them. Not the ones you created for your operational workload, only for the analytics. And what you do, replace them by a single non-cluster column store index. Now the beauty of this one is no application change. You're just creating an index. No application change, right? So you can even try today, you can say, I'm running my operational workload. I want to do some analytics on it. I'm going to create an index for now, try it out, and see how my operational workload handles. Is it impacting my operational workload? Or is it giving me good performance? You can see that very, very easily. Now, other thing is this index is completely transparent to you. You do not have to do anything. It is an index. You do DML operations on your table, index gets updated automatically, right? So that's the beauty of this index. And the key point is updatable. And that's where the significant amount of work we had to do. So now the question comes, the last point is also very important. Now, when you do the query, right? I mean, the query doesn't say I'm analytics query or I'm OLTP query. Query is a query. Optimizer knows that this query will benefit if I run that query using column store index. Or this query will benefit if I run, right? So optimizer will choose the index appropriately. You don't have to worry about that. So I think the basic point I'm making is by creating a non-clustered column store index that is updatable, you are done. Your application operational workload continues to run as before. On top of that, you get much more efficient execution of your analytics. Right? So now, one question comes is how expensive it is to maintain. Okay, so I made some attempt. Let me spend some time on this slide. This is actually a very useful slide. So all of us know about the traditional B tree, right? This is a traditional B tree. So I did this. I said, okay, there are 3 operations that you do in a operational system. You insert rows, you delete rows, you update rows, right? So let us see what happens in each of those cases. So the first case is when I'm inserting a row, it gets inserted into a B tree, right? In non-cluster column store index, it just goes into that yellow thing I was showing you. That is a row store. That's a B tree. It just inserts there, right? So it is exactly like that. There is no difference, right? Insert is an insert. It goes into traditional B tree, or it goes into the row store. I'm going to call that as a delta store. It goes into the delta store, which is organized as row store, okay? So it goes there. Now, if you look at the delete, when I say delete some row from this table, guess what? A index is used. It seeks into the row and then marks the row deleted, right? So here, if you look at A, it says seek the row. Now, if I want to search for the row in column store, there could be multiple delta stores because if rows are coming at a very fast pace, I may not be able to compress all of them quick enough, so it could be multiple stores. So what we do is we need to search for the row in those delta stores, okay? And so in the worst case, you will search through all the delta stores. So that means the cost of delete is higher with column store. If you found the row, then you have to delete it. The interesting thing about one is that if you found the row in the delta store, the delete is exactly what you do in a traditional B tree. But if you found the row to be deleted was compressed, then what we do is we do not change the compressed data. We keep it as compressed. It's read-only. What we do is we mark in another, it's not a table per se, but it is a place. We say that this row is deleted, okay? So what happens now is you have a column store where you have rows that are inserted and the sum of the rows that are deleted, all right? So when you do a query, we figure out all the rows that should be returned and then filter the rows that were deleted. You see what I'm saying? Because if I had 100 rows inserted, I deleted 10 and I run the query on all the rows, it will only return you 90 rows because 10 were marked deleted. It will remove them through the query processing. So that's that, right? Update is done as a delete followed by an insert. So in a column store, update is a delete followed by insert. The cost is exactly the same. So what you should see here is that okay, I think I should do this. Okay. So those red things that I'm showing you, these are the ones that are adding more cost to maintaining a non-cluster column store index. You all agree? Because this is more expensive because you have a traditional B tree index and now you replace that by a column store index, there is some additional cost. So now the question is, if I was running my operational workload and I created an NCCI or non-cluster column store index on it, I'm paying this additional cost. So where is the promise that your operational workload is not impacted? It is impacted. You see that? Okay. So what we do is we provide some ways for you to control that cost. So I'm going to show you the same table that we had before. And let's say for the DML operations, what you do is you create, just like before, a non-cluster column store index. You see that? The only difference is that it is filtered. You see that? Like there is no column store index on this part of the rows. Okay? Now, we consider this data to be hot. Okay? So imagine this. If I had a table and I said this data is hot for me and this is cold, I'm going to create the column store index only on the cold data. Okay? Now, what it means is hot data by definition means that's the data that is being pounded on in my operational workload, right? Now, if there is no column store index on that data, I'm paying zero cost for that, right? That means by doing this, I'm not paying any cost for my hot data, so my operational workload is not impacted. The data that is not so hot, yes, there'll be some additional cost, but that is not so hot data, I don't care, right? Now, when you do that, the SQL Server knows when I do an analytic query, not only it has to search in the column store, which is the cold data, it has to search even in the hot data because you want real-time analytics. So what happens now is your analytics queries is running transparently to you. You don't know. I mean, you don't care whether data is in a column store or hot. You want the data to be back in the real time. So what happens is when you run the query, Optimizer will run the query both on the column store as well as on the hot data. Now, since part of the analytics query is running in the traditional row store, that means the cost of query will be higher, right? Because it is not taking the advantage of column store. So here you have a dial. You can say, I want to minimize or eliminate the impact on my operational workload. I will say hot data and cold data. I will have my column store on the cold data. So I guess I'm going to pay more cost. My analytics will be slower, but at least my operational workload is not impacted, right? So that's the dial that you have. So the question is, what is the workload scenario where this makes sense? So I'll give you an example. You know, like an order entry system, right? People placing orders, right? And I'll give you a simple example, like when you go to Amazon and you place your order, right? Order goes through fulfillment, right? And ultimately it gets shipped. In fact, when order is submitted, you can change your order and things like that. So what we found in a typical order entry system, this is not Amazon thing, this is a traditional order entry system, changes approximately 10 to 12 times before it is shipped. Okay? Once the order is shipped, it does not change that much. Okay? So if I had a table, let's say order entry table, I can say I'm going to create a non-cluster column store index where the condition which I have in the blue, where order status is shipped. What it means is when I'm inserting my order, when I'm manipulating my order, there is no column store index overhead, right? So by doing that, you are able to strike a balance between the impact on the OLTP and the benefit of the analytics, right? So this is step number one. Now the second thing that you could do when you run the queries, okay? Now, yes, with the hot data, OLTP transactions are not seeing any impact, but I'm still going to run my reporting queries on that box, right? And that CPU cycles, that IO cycles have to come from somewhere, right? So as we talked about, the operational workload typically is a mission critical workload. It is highly available configuration, right? So what we have seen, anytime people have mission critical systems, they have always on. So what I'm showing you here is that you may have always on configuration, which is SQL Server feature that we introduced back in 2012. So you have a primary replica where you're running your operational workload with non-cluster column store index, all right? And then you have secondary replicas. In this case, I'm showing you 3 replicas. I mean, it could be just one, right? It could be 2, whatever not. So now what you can do is you can run your analytics on the secondary. Now imagine this, right? You have created a non-cluster column store index on the table with hot and cold configuration. So you're not paying much cost in the OLTP. And then you move your analytics queries to the secondary. So now you have eliminated both the query processing cost, as well as if it was generating some blocking, you move everything over to the secondary. And that's how you can get almost a whatever performance you had before for your operational workload and get almost the same performance after creating column store index. Any questions on that so far? You guys have been quiet, so I'm not sure whether. Okay. So, question, sure. Let me go back. That's right. That's right. Right. So I think my assumption is if you have your mission critical operational workload, I cannot imagine it is not under high availability configuration. Right? And if you are using always on configuration where you have readable secondaries, you create your column store, non-cluster column store index filtered on the primary. That's right. There is a question here. Yes.
Yeah, so if creating the column store with the filter, wouldn't you then still need all of the other indexes, the operational, and the transactions that are debugged?
That's right. So question really is, the column store that you created, it is only for analytics. Whatever indexes you had for your operational workload, we are not changing those. Those have to be there. Yeah? Yeah, exactly. Let me just take a question there. Yeah? That's right. That's right. So I think the point is being made is that I can do transactional replication where I'm, instead of having always on configuration, I'm replicating my data from the source and I'm going to create a column store index. I think that is true. You could do that, right? That means you have a more complex configuration. And some of the challenges with replication is there's a limitation in terms of the transaction throughput, right? Most common deployment that we have seen for high availability is with always on. But I think your point is well taken. Yeah. Question there? That's right. So you bring a very, very important point that the column store index creation as well as rebuild is offline. Okay. Okay, it is offline. So if I'm running on a operational system and if I have to rebuild my non-cluster column store index, that means my operational workload will have a downtime. Agree? So the question comes, why do you have to rebuild your column store index? Typical scenario is that my index got fragmented. I mean, this is if you have a B tree, you rebuild indexes because of fragmentation, right? Right? You don't do anything else, right? In a column store, what is a fragmentation? Fragmentation is you delete some rows. Now, as I talked about, when you delete a row in a column store index, the row is not physically removed. We just store information somewhere that this row is deleted. Okay? So over time, let's say I deleted 60% of my rows. Or if I updated 60% of my rows, because update is done as delete, insert. So suddenly what you see is 60% of the data is actually orphaned. I mean, it's not used. It is deleted, but it is sitting there. So that I call a fragmentation in a column store. So what we are providing in 2016 is an online defragmentation of the data. So what we believe with operational analytics scenario, if your index gets fragmented, you just do alter index, reorganize. It will remove the deleted rows online. Okay? Last question, then I will do the demo. Yeah. That's right. Yeah, right. So when you first create your non-cluster column store index on your operational workload, you will incur a downtime in the sense because it is going to be offline. Yeah. A question?
I'm just going to ask you, is it right to understand the backing of the transactions in the column store index that are to be updated to the main column store, the ever repository component? Sounds an awful lot like the memory map index. Sounds an awful lot like the equation memory map table. Is that the right type of architecture you've got going on there with the back
Okay.
why you get column store index.
Okay. So let me see if I got your question right. So let me answer this way. The column store is just an index. Okay. It is persisted just like an index, except we store the data a little differently. So anything that is compressed, we store as lob columns, like lob, the text columns. That's how we store it. When you query it, we bring the data from the disk into the buffer pool just like any other index. So there is no memory mapped file in that sense, yeah. Okay. So what I'm going to do is I'm going to show you a very, very simple demo. It is not fancy, but I think it's going to be give you some flavor of what's going on. Okay, so let me shift to my machine. I think I typed the password wrong. So what I have, I think while it is going to reject me, what I have is I created a table with very few columns, and I'm going to insert 2 million rows into that table, and then I'm going to create a non-cluster column store index, okay? And then I'm going to run the analytics with and without column store index to show you that analytics goes faster, okay? And then what I'm going to do is I'm going to show you the real-time analytics as well. So now this time I should type it correctly. Okay. All right. So what I'll do is, I think this database does not exist. I'm going to create this database. Everybody can see in the back? Okay, good. So the database is created. And notice I'm creating an in-memory OLTP database. The reason is I want to use the same database. I can actually create a column store index on in-memory table. I mean, that's a huge thing for us. And I'm going to talk about that immediately after this demo. So I create the table, create the database. Then I'm going to add a memory optimized file group, which I don't need for this demo, but I have added it. I'm going to use this thing. And the table does not exist, so I'm going to create a table. So I'm creating a very, very simple table. Okay, this table, of course, is not your traditional table because you'll have more columns, but let's just create this table. And what I'm going to do is I'm going to create a unique cluster index on it. And now I'm going to insert 2 million rows. Okay, it should take around 15, 20 seconds, maybe 30 seconds. So what I'm doing is I have a table. I'm trying to simulate the environment that you have, where you have a OLTP workload running. You have some data existing on it. And now what you do, you come and create a non-cluster column store index on it. So it is still going on. It should stop very, very soon. And then what I'll do is, while it is doing it, I'm going to create a non-cluster column store index, which is here. So all I'm doing is I'm creating a non-cluster column store index on 3 columns because I do not need analytics on the 4th column. So I'm just creating 3 columns. Okay, this should come through very quickly. So I'm creating a non-cluster column store index on a 2 million row table. And I'm going to show you how this data looks like. And I'm going to go here and let me first connect it. It won't find it, so I go to the database. So notice let me just do this. So what you see here is that this non-cluster column store index has, if you count the rows, these are 2 million rows. It has 3 compressed row groups, okay? Because each compressed row group is around 1 million rows. I talked about that. But what happened here, I inserted 2 million rows and I got 3 compressed row groups. Why is that? So what happens is when I'm building my non-cluster column store index, it is running in parallel. So what happens is there are multiple threads. So one thread got 1 million rows. Other 2 threads were fighting for the rows and they got half the rows each. So that's why I got 3 compressed row groups. And if I look at the property, this is, by the way, new DMV that we created for column store index in 2016. So it says residual row group. That simply means If I was doing parallel index build, I got some residual things, okay? So that's that. So now what I'm going to do is I'm going to do some analytic query on this, okay? I'm going to enable the time, and I'm going to set my isolation level to read uncommitted. And the reason I'm doing it is because I do not want any blocking while I'm running my operational workload. Now, interestingly, in 2016, we have implemented snapshot isolation and read committed snapshot with column store technology. It was not available in 2014. In fact, in 2014, you could not offload your reporting workload to the secondary. But with 2016, you can. So now, I set the isolation level to read uncommitted. I'm going to use my database. And now let me first run the query. Okay, I'm saying give me average of units sold for the whole table. I'm going to enable my query plan on this one. Right? Let me run this guy. And notice it chose the column store automatically because it knows it is scanning the whole table. I'm doing some aggregate things. So this is one point I want to make is SQL optimizer will choose the column store when appropriate. Right? I'm sure there are situations where it did not choose the right index, and you have to figure that out. But in general, it will choose the right index. All right. Now what I'm going to do is I'm going to run the query, same query. I'm going to first clean the buffers. I'm going to run the same query with cluster index, which is a traditional B-tree index I have in my table, and also the non-cluster column store index. Okay, let me run these queries. And what you will see is that if I look at the execution plan, the first plan, because I force the index, right, it is using cluster index. In my second plan, it is using column store index. Right? Now let us look at the execution time. So I go here, and you will see that the CI, the cluster index, took 464, and the column store took 111 milliseconds, right? So it is 4 times faster, right? From 464, same query, same table, with a non-cluster column store index, I could process the data 4 times faster, right? It's huge in that sense. And I think other thing to notice is some of you who know column store at a deeper level, notice that I ran this column store query in the batch mode. If you see the thing that I see, the third row from the top, it says batch mode. The batch mode execution is actually the secret sauce for column store. What it does is, when you run a query on column store, and it is processing lots of rows, right? So what it does is, instead of processing 1 row at a time, it processes 1,000 rows at a time, approximately. So with that, it gets order of scale magnitude benefit. We have seen with the batch mode, you get 4 times better query performance compared to if I run the same query with column store at 1 row at a time. So that's what you get. So now what I'm going to do is I'm going to run more inserts, okay? I'm going to run more insert. I want to show you the real-time analytics on this. And I understand this is not the high-end demo. So what I'm going to do is I'm going to insert additional 2 million rows, okay? And while it is inserting it, I want to do queries, okay? That's what I want to do. So I'm going to run it here. Execute. It's running. And now if I go to my analytics, I want to run the using NCCI, right? So I run this one, 1258, 1259. So what I'm trying to show you is, while the DML is running, I'm running my analytics, and it is running fine, right? Now, clearly what I can't show you in this workload is what is the impact on the OLTP and what is that. But what I wanted to show you at least is that you can run analytics as well as DML at the same time. Okay, question? Right. The column order question is, does the column order matter in the creation of a column store index? Answer is yes. And I think the reason is a bit involved. Let me try it here. Okay. So imagine this. You have a fact table. Okay. 100 million rows. Let's say that. Now we are grouping rows by million rows, right? So I have 100 such groupings. Okay. Now, if I do my query on certain column more frequently, so I say, give me the data for this company ordered by quarterly sale and whatnot. And if that data was sorted on the company, I do not have to read all those 100 units that I talked about, right? It may be just one or two. Okay. So that's where I think you get the performance benefit. A common example that we have seen is the data that comes into the system is coming in the date order time, right? So it naturally orders that way. So then you say, give me the analytics on last week, last month. And if I have a 10-year worth of data, then you know the last month data is just in small. So order does matter. Yeah. Your question?
To use a DDL statement for which the column index is involved, how does it affect the index? You have to do a reorg or
Right. Can you ask the question again? I got distracted. I was looking at the watch. I said, maybe you're running out of time. Sorry.
if you do a DDL change on a column that is involved in your column index,
Right.
how does it affect the index? You have to do a reorg on the table?
Right, right,
You have to do
right.
context test.
So I think the question is, if I create a non-cluster column store index on, say, 3 columns, and I add a new column to clearly,
You change a column.
okay, you change the type. Okay, if you change the type, then I believe you have to drop the column store index and recreate it. I think that's the limitation we have. But I need to look into that again, all right? So I think, as I said, the demo is a very simple demo, but I wanted to show you how you create column store index, why it is faster than your traditional B tree, right? And you can do real-time analytics while the data is going on, right? And interestingly, we can do the same thing with in-memory OLTP tables, okay? So let me go there. So I'm going to stop my workload here. And I think this is done. So one thing I want to show you again. Remember, this is what I had before, right? When I created the non-cluster column store index. Let me run that query again and see what I see. So notice, this is very interesting. What happened is I added 22 million rows more, right? You see the second row, it says open. So this is sitting in the Delta store. This is still not million rows, so it is not compressed. And the first one got compressed. So what happens is, as you're inserting rows, the rows are coming in, there's a background thread that is compressing this data. So from your perspective, all these things are happening in the background without involving any action from you. Okay. So now I have 15 minutes. I'm going to go and talk about what do we do for in-memory OLTP. So, okay, I think this thing is not working, so I'm going to try this. Okay. So what we do for operational analytics with in-memory tables. So what we are providing is you have an option to create column store index on disk-based tables or memory optimized tables. And the reason it is important is this. A lot of people could not migrate their application to in-memory OLTP because of functionality limitation, or they just could not change it, right? So what we wanted to do was provide a solution so you do not have to change your application. So you're running on disk-based tables, you create a cluster column, non-cluster column store index on that, and you're fine. If you have migrated a workload to in-memory OLTP, you can create column store index on that, and it works fine. So you don't have to make any changes. So this is available on the in-memory OLTP. Now, this is something unique in the industry. If you look at our competition, everybody provides column store index on disk-based tables. Microsoft 2016 is the first commercial SQL server or database server that combines both in-memory OLTP and the in-memory column store. So this is basically both OLTP and analytics on steroid. And this is actually, we believe, is a winning combination to deliver high OLTP as well as a very compelling analytics performance. So I put a different picture for a hackathon or in-memory OLTP. What you see here, how many of you know about in-memory OLTP? This came out in 2014. It's like 50%, right? So you have two kinds of indexes. You have hash index, which I try to show over there, and you have range index, right? Even though they're sitting on parts of the data, but they're for the full data, right? I just wanted to show them differently. So this is your operational workload running on in-memory OLTP tables, right? So what you do is, if you want to do analytics on it, you create a updatable column store index on in-memory table, okay? Now, remember we talked about a delta store for the traditional thing? For this scenario, there is no delta store explicitly. What we have is, there are certain number of rows that are sitting in in-memory table that are not yet migrated to column store, right? We call that as tail. So the tail is the delta store for in-memory OLTP, okay? So these are the rows that are in the row store, not moved to column store, okay? Other thing that you see, those things that I'm showing you in orange, the DRT stands for deleted rows table. So what happens is, like I said, when you delete a row in the column store, it is not really removed. It is just marked as deleted. So we have this deleted rows table that tracks which rows are deleted, all right? So these structures get created automatically, right? The tail index, because we need to find out what the rows are in the tail index, right? In the deleted rows table. And then everything just works like before. I can run a query, and if the query optimizer chooses that this query needs to use column store index, it will go and use column store index. So there are a few limitations on this one. I want to walk you through those things. The CDP2 limitation, this is the build that will come out soon. You can try these features yourself. First limitation is only for in-memory table. You cannot create a column store index on a in-memory table, on an existing in-memory table. You have to create column store index as part of create definition. Now, that simply means if you were running your OLTP workload and you want to create a column store index on it, you just cannot create like that. You have to first migrate the data out and do that. And this is something we will plan to address in the CDP3 timeframe, but this is the current limitation. And second limitation that we have is all the columns in your in-memory table must be included in the column store. Now, this is not the restriction on disk-based non-cluster column store index. You can choose any number of columns that you want. These are the two limitations, and this is something that we are working through. Now, as I talked about, there is no explicit delta row group. The rows are sitting in the tail, okay? Now, the interesting thing about that one is, if the rows are sitting in the tail, and if you're modifying any data there is no column store index there, right? So there is no impact. This is just like a hot data, okay? Now, what happens is there's a background task that, just like in a non-cluster column store index, it moves data from the tail into the column store index. And if you install CTP2 build when it comes out, that thread, what it does is, it migrates only those rows that have not changed for 1 hour, and in a group of 1 million rows. Okay, that's what it is doing it. Now, deleted rows table, I already talked about. It tracks deleted rows. Other important thing to note here is the column store that you create on an in-memory table must live in memory. Now, this is not the requirement for disk-based column store, but it is a requirement for in-memory OLTP. Now, one would think that is a lot of memory for me, right? And our rationale is, if you have in-memory table, the whole table must live in memory, right? And the column store gives you 10x compression. So essentially, you are adding 10% cost to your memory, and now you can do operational analytics on it. Okay, so that's what we have. And key thing is, once you have column store index, there's no index changes needed. There's no application change. So I want to walk through the same table that I had before, and I'm going to compare the cost of maintaining this column store index on in-memory tables. So as you can see, when I'm inserting a row, it is directly going into the hot part of my table, right? I want to go back to the previous screen so that you will know. Sorry. Okay. So when I'm inserting the row, it is only going here, right? So there is no overhead. Now, if I want to delete the row, if I found the row in my hot data, there is no overhead, right? Because I'm just going to delete just like before. But if it was not in the hot data, it was in the compressed, then I have to do a insert into the deleted rows table. Agree? That's what I have to do. Now, update is very similar, which is I delete and then I insert. So those are the two things, red blocks that I'm showing you is the additional overhead. So now the question is, how do I manage the impact on my OLTP workload if I create a column store index on my in-memory table, right? So what I'm showing here you is the same picture that I had in the previous slide. And what you can do is, you can, if you could keep your hot data in Hackathon only for a day or for a week or whatever, right? I mean, you know that your workload, the data stays hot for a few days and then it becomes cold, right? So suppose you knew this property of your data load, right? And in fact, we did a customer survey. We found around 30 to 40% people said in their workload they know the data is hot only for a certain duration in time, okay? So if you knew that, what you could do is you could play around with some options, and I'm going to tell you some options. This is a workaround in CTP2, and we are working to provide an option on the table level to say my data stays hot for certain duration, okay? So what you can do right now is you use the trace flag 9975, which will disable auto compression, okay? And then what you do is you define that my data will be hot for a week or for 1 day. You run a stored procedure that will compress the data after 1 week, okay? After 1 day, whatever the duration you have. So that is a functionality we want to provide, but this is what you can do in CTP2 today. So what it means is now I can control how long the data stays hot for me. That means I can control the cost of maintaining my non-cluster column store index on in-memory table. And for the queries, just like we were able to offload the queries on the readable secondary, I could do exactly the same. I have a in-memory table with column store. I have a readable secondary. I can offload my workload. With that, I wanted to summarize some key points, and I'll take any questions you have. So first thing is, with operational analytics, you can do analytics in real time with minimal impact on your OLTP workload and no data latency, right? This is a huge, huge win if you want to do real-time analytics. And SQL Server 2016 provides you options to control the cost that you need to pay for your OLTP for column store. So good balance you can choose depending on your workload, very important. And the last thing, which is actually very key, is you can get operational analytics without changing anything in your application. Okay. So I hope it was useful for you in terms of presentation and you understand the technology. Any more questions? I have 5 minutes. I'll be happy to take questions. So I'll take you first. Yeah.
Does column store work with the stretch memory, the stretch database functionality that you're using column store index of data?
Right. So currently the column store index is not. Question is it integrated with the stretch database? I think it is not. Okay. I'll take a question here, then I come there. Yeah.
Trace flag and manual compression available on the disk space or just the in-memory? The trace flag and manual compression to overwrite defining when?
Right.
Do that on disk space as well, or just?
No, just, yeah. So currently there is no way to control. I think it's a good question. Can I control the time thing for disk space tables? No, not yet. Okay. Question?
So with that storage feature to force compression,
Yeah.
you give it a parameter saying if it's older than a certain.
What you do is when you run the procedure, it just compresses everything. Everything in the tail, it gets compressed. Okay. Yeah. So we need to work on it. But I'm just trying to show is there are ways to control the hot data. Yeah. Anything? Okay, yes, sir. That's right. That's right. Numbers would have changed. The question really is, the string data does not compress very well, right? And also we maintain some level of dictionary. So yes, compression will be different. Yeah, but like in this case, since the value was same, they compress very, very well. Yeah. I'll take a question here and then I'll come to you. Okay, question. The optimization of joins. So the column store, right? Yeah, the column store works very well with joins because the thing is, in fact, because of batch mode processing, the whole tree is optimized. So you will see. I've not shown a very complex query, but yeah, it works very well with optimized. Right. I mean, create, right? Not rebuild. Because if you, I mean, no. The column store index, actually, that's a good point. The column store index on in-memory table is only for persisted in-memory tables. That's right. So yeah, when you restart, it has to be created. Exactly. It will, not only it will take memory because the column store index lives in memory, right? That's right. Yeah, I think they'll be at cost. And I don't have a data on that one, but you're right. When you have a column store index on an in-memory table, when you restart the SQL server, it will, yeah. Yes, sir.
Can you create multiple column store indexes?
No. We only allow one column store index on the table. You can include many columns, and that should suffice.
Does it really matter? I mean, can you add all the columns in there?
You can.
Does it have any rows and columns?
No. So the beauty of the column store index is you create, but in the query time, you're only getting the columns that you need. So there is no. There was a question on that aisle, or no? Okay. This is the last question because I know there's a big presentation coming very soon.
Fragmentation means a little bit something different.
Right.
Is it surfaced in the same way?
It is surface in the sense, it is not surface in the same way. I mean, the fragmentation for column store means deleted rows. Like you have a lot of wasted, yeah.
Like, you want to reorganize it over a certain threshold. How do you?
That's right. So there are DMVs available that you can find out how many deleted rows are there. You can decide.
It's just different.
Just, yeah, exactly. Well, thank you so much. Thanks for coming. Yeah.